All right, here we go, folks. Um, so we're going to go through the calorimetry here, the note, um, and then we should hopefully have some time to work on the homework after. So calorimetry, exactly if you break the word down, like calorie, talking about heat and energy, and then imetry is study of, so the study of heat flow and heat measurement. We've got Okay, so the first thing dealing with is called heat capacity. The amount of heat needed to raise the temperature of the substance by 1 degree Celsius. Um, and then a term called specific heat, which is the variable C sub S, is the amount of heat needed to raise the temperature of specifically 1 gram of the substance by 1 degree Celsius. So we've already mentioned this in a previous notes section when we were talking about what a calorie is. But this is the specific heat again. So, for example, the specific heat of water is 4.184 joules over grams degrees Celsius is the label. So, and that's, so that is always, that should always be the specific heat. Like a specific heat is a constant for a substance. So like water should always be 4.184 joules over grams degrees Celsius. Okay. Which means that it takes 4.184 joules of energy to raise 1 gram of water by 1 degree Celsius, temperature-wise. Okay, so we have this equation, CS equals Q over M times delta T. I've written out the variables here, what they are. C sub S is specific heat. Q is heat in general. It's the amount of energy. Okay, so like CS is it's like an amount of it's amount of heat per gram degree Celsius. It's a constant. It's like a ratio, kind of like density. Q is the overall amount of heat. So just flat out amount of heat energy. Okay. I guess I could write this by him too. C sub S, the label is typically joules over grams degrees Celsius, like we had there. Q is heat. The heat label is typically joules. Now it could be something else like calories, whatever we did convert it, but you want it in joules to be doing these equations. M is mass, that would be in grams. Delta T is change in temp, which we typically want in degrees Celsius.
How do you remember all this stuff?
Years of doing it. Just kind of pounds it into your head. So, all right. So the best way just to do it is really just to do problems. So let's do this first one here. What is the specific heat of nickel if the temperature of a 32.2 gram sample of nickel is increased by 3.5 degrees Celsius when 50 joules of heat is added? So just to sort of organize so we know what we have, I'm going to write some variables over here. What is the specific heat? So we're looking for the C sub S. Okay. If the temperature of a 32.2 gram sample, so that's my mass, 32.2 grams, okay, so the temperature is increased by 3.5 degrees Celsius. So make sure you're reading that part carefully. I'll explain why in a little bit, but so the increase by, so that's our change in, because it's increased by that amount, change in temp, 3.5 degrees Celsius, when 50 joules of heat is added. So this is just heat in general, so that's our Q. All right, so if we look at what we have, we're looking for CS. We've got these, so it's pretty much just straightforward plugging in and solving. So C sub S equals Q on the top over mass 32.2 times change in temp delta T. So that's
Wait, why is it 50 points there? Like, does that mean
the point here. Just really what that does is it forces it to have two significant figures for the answer. So delta T down here, so it'd be 3.5 degrees Celsius. Okay. And then you just plug it in your calculator. Now, one thing to be careful of when it's kind of set up like this is if you type it all in your calculator at once, make sure if you're multiplying these bottom two, either make sure you multiply them first and then divide, or if you do it all at once, put parentheses around it. Yeah, like 50 divided by parenthesis 32.2 times 3.5 and parentheses, something like that. Okay. What's that? Should be 4. Yeah, 0.44. Did you put parentheses?
Yeah. Oh, I put them because I did 32.2 and then close parentheses.
Oh.
And then parentheses again.
Yeah, you got to put them. You got to put them together.
Now I got 0.44.
Perfect. There you go. So C sub S equals, and then significant figures like we're talking. It's 3, 2, and 2, so it's 2. So it's 0.44. And our label for CS is kind of weird because it's a constant technically, or usually. So it's joules over grams degrees Celsius. That's the whole label. And that is our answer. Okay.
Now, that delta symbol, that just means a change in.
A change.
Okay.
Yeah, correct. And I'll show you as we go on here something with that. So, okay. Any questions so far on that? All right. So part C, heat transfer between reactions and surroundings. Heat, or energy in general, cannot be created or destroyed. So any heat lost by one substance needs to be gained by another. So this goes into the reaction, or into the, this leads us to this kind of equation, this idea. Heat of the reaction is equal to negative heat of the surroundings. And it can be written like this: Q of reaction equals negative Q of surroundings. All it says is whatever one thing gains, the other thing has to lose, or vice versa. So imagine, you guys know the cold packs that you can break and then you have the reaction, right? So you have one of those and you put it on your knee or something. Okay. So the reaction is absorbing heat. It's pulling it in, right? Where's the heat coming from? Your body, the surroundings of the reaction, right? It's pulling it some from the air, some from your body, whatever, but it's absorbing it from the surroundings. So the heat that the reaction that the cold pack is gaining has to come from somewhere. It has to come from the surroundings. So whatever the cold pack gains, the surroundings have to lose. Okay, and if you think about the opposite of that, like a hand warmer, it would be the opposite, right? You have the reaction going, the reaction is kicking off energy. So whatever the amount of energy is that the hand warmer, that reaction loses, the surroundings then have to absorb. Does that make sense? So that's all this is saying. So it's whatever the reaction gains, the surroundings will lose, or if the reaction loses, the surroundings will gain. That's all it is. It'll be the same amount, just one positive, one negative. Any questions? All right, let's flip it. All right, part D, calculating heat. So this is actually usually how we look at the calorimetry equation. Usually it's like this. This is the same equation as this one. It's just rearranged. So if you ever hear me say this, It's pretty common. I did not come up with it myself. It's people say it all the time. It's this equation as Q equals MCAT. It's because it literally looks like MCAT with the delta T. So if you hear me say Q equals MCAT, that's the calorimetry equation. Okay. It also kind of helps you remember the equation. So, and again, I've put the variables. The variables are the exact same as on the front page. The variables are the same thing. Q heat, M mass, C sub S specific heat, delta T is change in temp. Okay. So let's do this problem. Again, same thing. I'm just going to organize the information I have. The specific heat of water is this, so that's C sub S, 4.184 joules over gram degree Celsius. How much heat is required? So how much heat, that's our Q, that'll be what we're looking for, is the Q, to raise the temperature of 5 grams of water, so that's our mass, to raise the temp by 3 degrees Celsius. So that's our delta T, because that's how much the temperature is changing. We want to change it 3 degrees Celsius. So far, so good? Okay, now again, this, with what we have and what we're looking for, it really just becomes a plug and chug problem. We're going to plug it into that equation. So Q equals our mass. And watch your labels on these. Okay. Our C sub S. And our delta T. Okay, so we just multiply these together. And if you look at the labels, look what happens here. So like grams is on the top and grams on the bottom there, so it cancels. And if you set it up right, this should happen. So degrees Celsius cancel. So we're left with joules, which makes sense because we're trying to find heat energy, the Q. Joules is an energy label, so that works. So we just multiply them together. Significant figures are 2. We don't use CS in significant figures because it's a constant. So it'd be these two things. So we got 2. So 62 points. So it's like 62.76 becomes 63, and our label we're left with joules. How do we feel about that? Make sense? All right. Good. Okay. Let's go on to the next example with still using this, but you can also be asked to find either the initial or final temperature for a calorimetry problem. For this, you use Q equals MCAT with the following equation. Now, delta T equals T sub F minus T sub I. Okay. Delta T is change in temp. T sub F is the final temp. And T sub I is the initial temp. Okay. Now, just so you guys know, there are some also where it's just a Q equals MCAT, but they give you an initial and a final. Okay, and you have to subtract to find it. So like, for example, on the homework, the first one you're going to do gives you, it says to raise the temperature from 13.1 degrees Celsius to 40.5 degrees Celsius. So this is your initial temp, that's your final. To get your delta T, you would subtract final minus initial. Everybody good on that? Makes sense? Okay, so this one is a little more complicated. This one's a problem where we're finding one of these parts. So let's go through it. I'm just going to organize my information as I go through. So 7.23 gram sample of water. So I've got that's a mass. Uses 774 joules of energy. So that's my Q, because that's straight up energy. Okay. To raise the temperature of the water. Now, here's where you have to read carefully. To raise the temperature of the water to 42.9 degrees Celsius. Not by, to. So the 42.9 degrees Celsius is our final temp. That's what we're getting the temperature to. Oh, sorry. Is it off the? There we go. So T sub F, our final temp, 42.9 degrees Celsius. It's not delta T. You got to be careful. Everybody good with that? Understand why? Okay. If the specific heat of water is, so that's our C sub S, 4.184 joules over grams degrees Celsius. What was the initial temp of the water? So we're looking for T sub I, initial temp. All right. Now, if you get a problem and it seems a little more complicated and you're kind of like, okay, I'm not sure what I need to do to get, to this.
Was there an F after the T?
That's final temp.
Oh, okay.
So T sub F is the final. T sub I is the initial or beginning. So if you're not sure, one thing you can do, sort of a problem solving strategy, is sort of logically work your way backwards. Start with what you need to know, like what you're trying to figure out, and ask yourself what you need to find that. So for example, we're trying to find T sub I, right, our initial temp. Well, what are we going to use? What equation are we going to use to do that?
Delta T equals TF minus TI.
Good. We're going to use this one, right? That's the one with T sub I in it. So what does that mean? Well, that means if we're looking for TI, we need to have, in order to use this equation, we need to have TF and delta T, correct? We need to have those two things. So let's look and see, do we have delta T or TF? We have TF. We do not have delta T. So in order to do this, we know we're going to need to know delta T. So I'm just logically working my way backwards to see what do I need to have to get there. Okay? So I need delta T. So obviously I'm not going to use this equation to get delta T because we don't have TI. So we're going to look, well, can we use the Q equals MCAT? So delta T is in that, so that would work. Let's see. To do that, then we would need Q, M, and CS, right? Let's see, do we have those? Q, M, and CS. We do. So we can use the Q equals MCAT to find our delta T. So let's do that. So Q is 774 joules. The mass, 7.23 grams, times our CS, 4.184 joules over grams degrees Celsius, times, and we're looking for delta T. So I'm going to leave that like a variable. Everybody okay so far with where we got the numbers from and why they're in the spots they're in? All right, so we just solved this. You can do it all in one thing if you want. I'm going to take this just to kind of show for the notes. I'm going to multiply these two together first. We get 7.23 times 4.184. We get significant figures to be 3, so it's 30.3. And our label, at this point, if you look, grams have canceled. So we're left with a label technically here of joules over degrees Celsius times the delta T. Now to get delta T alone, we divide, right, because we're multiplying here. So we would take 774 divided by 30.3, and we get significant figures would be 3, so it's 25.5. And the label, the joules would cancel, so we're left just with degrees Celsius, which makes sense because we're finding our change in temp, right? Okay, so at this point, we've found our delta T. Okay, but we've got one of them, but we need our T sub I, right? So basically, this is like one of those algebra problems where you have like two variables, and you got to solve for like you solve for X, and you plug it into something else to get Y, or whatever. Like you plug X in. That's kind of what you're doing here. So we're taking this, and we're plugging this into this. The delta T equals TF minus T sub I. So we get 25.5 degrees Celsius equals our T sub F, which is up here, 42.9, minus, we're looking for T sub I. Okay, so this, we subtract to get the T sub I alone, so 25.5 minus 42.9. We get a negative 17.4, and you got to be careful. If you look what's left over here, it's negative T sub I. So the negatives cancel. So it's positive 17.4 degrees Celsius was our initial temp. All right, how do we feel about that? Is it making sense? Any questions? Okay. So that's where we're going to stop for today. We'll finish the rest later.